Most people hear the phrase nuclear battery and imagine a miniature nuclear reactor sitting inside a phone or a car. That image sounds dangerous and a bit unrealistic, but the devices now being developed by companies and research organizations are usually something very different. Many have no moving parts at all. They do not create explosions, chain reactions, or giant bursts of heat. Instead, they slowly convert the natural decay of radioactive material directly into electricity. Some of these systems can continue producing power for decades without ever being recharged. That changes the purpose of a battery completely. Instead of maximizing short-term output, engineers are beginning to design batteries that survive longer than the machines they power. The reason this matters is simple. Modern electronics are spreading into places where replacing batteries is extremely expensive or nearly impossible. Satellites travel millions of miles from Earth. Deep ocean sensors can remain underwater for years. Remote industrial monitoring systems may sit in isolated environments with no maintenance crews nearby. Even medical implants inside the human body face the same problem. A conventional battery slowly drains until it dies. Eventually, someone must replace it. In many systems, the battery itself becomes the weakest part of the machine. Engineers have spent decades improving charging speed and storage capacity, but operational lifespan is becoming just as important. The basic idea behind nuclear batteries is surprisingly old. Scientists experimented with radioactive power systems in the mid-20th century. Some designs used heat from radioactive decay to generate electricity. Others attempted direct electrical conversion using semiconductor materials. The concept worked, but older systems often suffered from poor efficiency and difficult manufacturing requirements. Conventional chemical batteries also improved rapidly during the same period. Lithium-ion systems became cheap, rechargeable, and powerful enough for consumer electronics. As a result, nuclear batteries remained limited to specialized applications like spacecraft and remote monitoring systems. But modern materials, science is changing the equation again. Better semiconductors and more durable shielding materials are allowing engineers to revisit concepts that were once impractical. Please subscribe. One of the most important things to understand is that these batteries are not designed for high power output. That is where many people become confused. A lithium-ion battery in a smartphone can deliver a large amount of power quickly. A nuclear battery usually cannot. Instead, nuclear batteries specialize in extremely slow and stable energy production over long periods of time. Imagine a tiny stream flowing continuously for 50 years instead of a giant wave lasting 1 hour. That makes them unsuitable for energy-hungry devices like electric vehicles or gaming computers. But for systems that require only small amounts of electricity, they become extremely attractive. Many modern designs use radioactive isotopes that naturally emit particles as they decay. Those particles interact with semiconductor materials and generate electrical current. In some ways, the process resembles how solar panels convert light into electricity. But instead of photons from the sun, the semiconductor absorbs energy from radioactive emissions. Because radioactive decay occurs at a predictable rate, the power output also remains extremely stable. Organizations like NASA have relied on long-duration radioactive power systems for decades in deep space missions, since sunlight becomes too weak far from the sun. Some spacecraft traveling through the outer solar system are still operating today because their radioactive power sources continue generating electricity long after conventional batteries would have failed. This technology becomes even more interesting in environments where maintenance is difficult. Consider remote infrastructure such as pipelines, offshore platforms, or isolated weather stations. Replacing batteries in those systems creates major logistical costs. Maintenance crews, transportation, and shutdown procedures all consume money and time. If a battery can survive for decades, entire categories of maintenance operations become less important. The same logic applies underwater. Deep-sea sensors monitoring pressure, movement, or communication cables may operate in environments where battery replacement missions are extremely difficult. Medical technology is another area where nuclear batteries may become valuable again. Devices implanted inside the human body face strict reliability requirements. Pacemakers are a good example. Traditional batteries eventually require replacement surgeries, even if the electronic systems themselves still function properly. A power source capable of operating for decades could reduce the need for repeated procedures. Earlier generations of radioactive medical batteries actually existed decades ago, but advances in miniaturization and shielding may allow newer designs to become safer and more practical. Companies like City Labs have explored compact radioactive battery systems for specialized applications, where long-duration reliability matters more than high-power output. But these systems face major engineering problems that prevent widespread adoption. Radiation safety is the first concern people think about. Any device using radioactive material must contain it securely under normal operation and during accidents. That means engineers need shielding systems capable of surviving fires, impacts, corrosion, and long-term material degradation. Even when radiation levels are low, public trust becomes a major challenge. Consumers are unlikely to accept products they perceive as dangerous, especially after decades of fear surrounding anything labeled nuclear. Power density is another major limitation. Nuclear batteries really do excel at longevity, but they usually produce only tiny amounts of electricity compared to chemical batteries. That, of course, severely limits their use cases. For instance, a smartphone or a laptop consumes far more power than most current nuclear battery designs can realistically provide. So, engineers tend to focus on specialized low-power systems instead of mass-market electronics. Some researchers are attempting to improve semiconductor efficiency and energy conversion methods, but the physics of radioactive decay still imposes hard limits on the available power output. There is also the issue of cost. Manufacturing radioactive power systems requires specialized facilities, strict regulations, advanced materials, and long testing procedures. Meanwhile, conventional batteries benefit from enormous industrial scale. Billions of lithium-ion cells are produced every year for things like phones, tools, vehicles, and all sorts of consumer electronics. Nuclear batteries simply cannot currently compete with that manufacturing ecosystem. The economics only begin to favor nuclear batteries when maintenance becomes extremely difficult or failure becomes extremely costly. Some organizations are trying to push the technology further. The European Space Agency, for example, continues exploring long-duration power systems for missions where solar energy becomes unreliable. Companies connected to nuclear engineering, including Westinghouse Electric Company, are also studying advanced compact power technologies for specialized infrastructure applications. Researchers are experimenting with new semiconductor materials, such as diamond-based systems, because they can tolerate radiation damage more effectively than older materials. After all, a battery designed to last decades must survive its own energy source without degrading too quickly. The most important consequence is not that nuclear batteries will replace every battery on Earth. That is unlikely. The real change is that they could enable categories of machines designed around extreme longevity instead of frequent maintenance. Space probes, infrastructure sensors, autonomous monitoring platforms, underwater communication systems, and long-life medical implants all become more practical when the power source stops being the weakest component. Instead of constantly recharging and replacing power systems, engineers may eventually build devices expected to quietly operate for most of a human lifetime without ever needing another charge. Please like and subscribe. Thank you for watching.